Welcome to this demonstration of the XADATU project of the FLUIDOS Open Call. This project extends the security and zero-trust architecture of FLUIDOS by integrating a decentralized XACML component for ABAC authorization, access tokens, and DLT accounting of authorization requests. The demo setup consists of two FLUIDOS nodes, a consumer and a producer as shown in the image above. Both nodes feature their own privacy and security manager to autonomously handle security, identity, and distributed access to the DLT. Also, this demo includes the components developed and integrated in XADATU, which are the PEP proxy and the XACML. The producer node also includes the REA API for resource acquisition, which is secured. The terminal on the left executes the demo and shows the different steps of the workflow, while the terminals on the right are the FLUIDOS nodes, the consumer, the producer, and the REA API of the producer. The first part of the demo is the enrollment. In this part, we start generating a decentralized identifier, DID, for the consumer node, which is stored in the blockchain, and the same for the producer node, whose DID is also stored on the blockchain. Once the DIDs are generated, the consumer requests a verifiable credential to its own privacy and security manager. As you can see, the credential includes a set of attributes that describe the consumer. This will be useful when defining policies in XACML, as we will see later. Once the VC has been generated, the last step of the enrollment section is to create a verifiable presentation, which is a tamper-proof package of a subset of the VC shared by the consumer to prove claims about its identity or attributes. The next part of the demo is the authentication and authorization section. From this point, the consumer is ready to send requests to the producer's REA. To do this, the consumer first checks if it has a stored access token, in this case, to request a list of flavors from the REA. Since this is the first interaction, the consumer does not have any stored access token yet, so it initiates the request process to obtain one. As observed, the XACML has determined that the consumer is not authorized to perform this action, as can be seen in the XACML logs. Additionally, it can also be observed that this authorization request has been recorded on the blockchain for accounting. To fix this, we go to the policy administration point to manage the policies. Here, the administrator has previously created the policies defined for the demo. If we look at the rule for retrieving a list of flavors, we can see that all attributes have the correct values. However, at the bottom, the decision set for this rule is deny, which is why the XACML is rejecting the request. To fix it, we change the policy to permit and wait for the policies to update. Once the XACML policies have been updated on the blockchain, we can retry the request to list the flavors. This time, the XACML authorizes the consumer, allowing it to obtain the access token and successfully send the request to the REA. If we decode the access token, we can see the different header values, such as the algorithm used or the key identifier with which the token was signed. On the other hand, in the token's payload, we can observe fields like the consumer's DID, the creation and expiration dates, or the resource that can be accessed with that token. Then, if we check the PEP proxy logs, we can see that the token sent by the consumer is valid, so the PEP proxy forwards the request to the producer. If the token were invalid or expired, the PEP proxy would reject the request. Then, we select the flavor 001. To create a reservation of this flavor, the process is the same. Once the access token is obtained, the consumer sends the request including the access token to the REA, and the consumer receives the confirmation of the reservation. Then, to make the flavor purchase, we follow the same process as in the previous steps. It can be observed that the consumer receives the purchase contract generated by the REA and signed by the producer. The next step is for the consumer to sign the purchase contract. As this is an internal request from the consumer, it is not necessary to obtain an access token. The same happens in the last step, where the signature of both the producer and the consumer is verified, thus proving that it is a valid contract. Finally, another functionality added by XADATU is the storage of authorization requests made to the XACML on the blockchain for accounting purposes. XADATU provides a REST API server with multiple endpoints that allow retrieving the stored authorization requests generated during the execution of the demo. If we access the blockchain database, we can see that, in addition to storing the DIDs, XACML policies and attributes, the blockchain is successfully storing the authorization requests made to the XACML. For more information about the XADATU project, please feel free to check the documentation or contact OdinS Solutions developer team. Thank you very much for watching the video.